Convolutional neural networks have been the most important deep learning algorithm for vision-related tasks for the last 15 years or so. But complex neural network architectures like these are often seen as black boxes that simply take some input, crunch some numbers, and then throw out a prediction. And while this criticism is largely accurate, there is still a lot that we can learn by simply poking around and try to pry open these black boxes. And the goal of this video is to do exactly that and develop a deeper understanding of convolutional neural networks and try to see them more transparently than some black box voodoo magic. And to do this, first we will understand what convolution even is and where this idea originally comes from. Second, we are going to explore a trained CNN by literally visualizing all of the features and kernels that they learn and try to wrap our human brains around what they are possibly trying to achieve. And finally, we are going to analyze the primary architectural design choices that have made CNNs so proficient to learn from image data. Welcome to Neural Breakdown, and let's get started. Simply put, the convolution operation inputs two different signals and then outputs a third signal that calculates the overlap between the two inputs. Let's understand how it does this with a very simple, intuitive example. Imagine that you are treating patients in a hospital. Each patient needs a 3-day treatment where they get 3 units of medicine on day 1, 2 units on day 2, and finally 1 unit on day 3. Let's put all of these dosage values in an array. Also consider that for the upcoming week, you'll get 1 patient on day 1, 2 patients on day 2, and so on till day 5. Let's also put these numbers in an array. Now, given these information, how can we answer the question, how much medicine will the hospital need for the next 5 days of this week? Well, this is exactly what convolution helps us to answer. Let's flip our dosage array and overlap the last value with the first value of our patient's array. What is the total dosage we need on day 1? Well, it's 1 times 3 equals 3. For day 2, we shift the dosage array by 1 step. Now the patient from day 1 gets his dosage 2, while the 2 new patients from day 2 gets 3 doses. The total dose we need is 8 units. On day 3, we shift by 1 again, and this time the patient from day 1 receives 1 unit, the patients from day 2 receive 2, and the 3 first-time patients from day 3 receive 3 units, adding a total to 14 units. On the next day, we repeat the same, but notice that now the day 1 patient no longer overlap any dosage unit because their 3-day treatment is now done. A couple of days later, the dosage window begins to advance away from the right side, indicating that there are no new patients coming. So nobody receives the 3 doses on their first day. After the overlapping finishes, we are left with this new output array that contains the total dosages required for each day of the next 5 days. So that is the convolution operation in a nutshell. The patient's array is often called as the input signal, and the dosage array is called the kernel. In a sense, we are scanning the kernel across the input signal and calculating their dot product at each location of the overlap. In machine learning, this output signal is also called as the feature map because we are essentially extracting high-level features about the input signal by transforming them with these kernels. And the sweet thing about convolution is that we can choose different kernels, and depending on what we choose, we will get different features. So for example, if you had a kernel like this, where there are 5 values and each of them are 0.2. Let's look at an example to see how this kernel will extract a feature map out of the input signal. At each overlapping point in the input signal, the values get scaled by 0.2 and then added. So if you rearrange the numbers a bit, it's just a formula for the average value of the overlapping area. At the next step, the kernel moves to the next location and averages this new area. So in other words, if we convolve any signal with this input, it just creates a moving average of a window size of 5. This is kind of like a signal blurring effect. What do you think will happen with a kernel like this? Well, this one simply outputs the difference between the adjacent elements in the array. So a convolution will detect places where the signal rises or falls. In other words, this is kind of like an edge detector. So the step by which the kernel advances in each iteration is also called the stride. In our example so far, since the kernel has moved by one position after each iteration, the stride was 1. But if we set the stride to 2, the kernel will move 2 positions after each iteration. It means that after the first overlap is computed, it will skip the second and move directly to the third spot and then the fifth spot and so on. And this results in a feature map that is half the length of the size of the normal feature map with stride 1. And because we are reducing the size of the feature map, this is a type of undersampling or feature compression. And the best part about convolution is that it could be extrapolated to 2D, 3D, and even higher dimensional inputs. So in 1D, the edge detector that we saw looked like this. It's just a 1D array. But in 2D, the edge detector might look like this, a 2D array. So let's apply the convolution of this edge filter on a chess king and see what it produces. And while that is still running, here's some exciting news. I'm happy to announce that this channel now has YouTube membership options as well as a brand new Patreon page. Members and patrons get access to all of the animation, slides, and code that have been used in all of my videos, including this one. And when it comes to supporting the channel, one member sign up is equivalent to watching like 500 ads. So do consider clicking the join button below to learn more. Also, if you are enjoying this video so far, please leave me a like, let me know in the comments, and don't forget to subscribe. I'm a very small YouTuber, so all this feedback literally makes or breaks my videos. So thank you for your support in whichever way you choose. You are magnificent. As you can see, we now have the outline of the king. The red pixels capture the positive values in the feature map where the image went darker from left to right, whereas the blue pixels are where the image went brighter. Here the kernel is a 3x3 grid with these 4 pixels turned to 1 and the rest to 0, kind of looking like an inverted C. At any given point in the overlap with the image f, we are going to multiply each overlapping pixels and then sum up. So in this case, only 2 pixels are overlapping, so the convolution value is 2. Let's repeat the process for the rest of the image. At this position, we will see that all the kernel pixels align perfectly with f, outputting a 5, indicating that here we do have the strongest overlap. If we had the letter E, for example, and run the same kernel, instead of 1 such point of strong overlap, we will get 2 such points. And if we run this kernel on an alphabet like I, the best overlap we get is just 2 because this pattern doesn't occur much in the letter I. And this means that the different kernels yield high numbers on images where their patterns occur frequently, while lower numbers where the pattern is absent. So with the fundamentals of convolution out of the way, it is time to look into how CNNs combine this idea of convolution and the concept of neural networks into one big happy family. Let's get into it. So if you take multiple different kernels, all scanning for various patterns independently and parallelly on the same input image, you basically get a convolution layer. A convolution layer is a collection of multiple kernels. Maybe one kernel in this layer is pattern matching a horizontal line and another a vertical line, while some other kernel is trying to capture an arc or so on. In a couple of minutes, we will be visualizing how these neural networks learn these kernels and how to visualize them. Also notice that the raw convolution is basically a multiply-add operation, meaning it is a linear function. And to train a neural network that is expressive enough to learn complex functions, we must also add some nonlinearity. The most standard nonlinear function to use with CNNs is the ReLU function. The ReLU basically converts all negative values to 0 and lets all positive values stay as is. Meaning that if at any location the feature map had a negative overlap, we would essentially say that the pattern is absent or 0 at that location. In this video, we will be training a simple CNN to predict handwritten digits using the MNIST dataset. I go into a lot more detail about the programming aspects of this project, including training and visualizing these networks for the channel members and patrons, along with full access to all the slides, Word documents, animations, and code used in this video. So do check out the description below if you're interested to join. So the first one I trained was just a simple single layered convolution layer with kernel size 5 cross 5 and just a single kernel. So it is extremely limited at what it can do. So here is the kernel it learned. The red pixels are the positive values and the blue pixels are negative values. An arrangement like this means that this kernel will have the maximum overlap when it finds pixels to its bottom left region. Let's see what feature map this kernel generates on the number 4. Well, the first overlap occurs here, the second and third one occurs here and there. Let's compare that with the feature map of the number 1. And you can clearly see how the network learns to differentiate between 4 and 1 and sees that for the number 4, you get 1 extra point of high overlap. The problem with having just one channel, though, is that the feature maps are way too limited in how much it can learn. This is a phenomenon in machine learning known as underfitting, where your network is too simplistic to capture all the high variance in your training data. The accuracy of this model is about 90%, but it drops to 60% if you're trying to differentiate between 0 and 3. And let's see why it confuses between 0 and 3 by running the kernel across the two images. Aha! The feature maps look extremely similar. Because the kernel only searches for this top right pattern, the arcs of number 0 and 3 confuses it. So let's try to increase the number of kernels from 1 to 4 and see what happens. Okay, so now we got 4 filters. Again, the blue values are negative and the red values are positive. The actual numbers are kind of creating a bit of clutter, so I'm just going to turn off the numbers and just look at the colors from now on. To intuitively understand what these kernels might be doing, we have to look at each of them and ask the question, what type of features in an image will overlap with these kernels perfectly? It requires a bit of imagination, but the first one looks like it tries to match a flat horizontal line and blank space above and below. Here is an example of the number 2 where this one activates. If we repeat this imaginative process for all of the kernels, the second one looks for a top edge, the third one is probably looking for some diagonal patterns, the fourth one is looking for top left corners. If we input an image, this team of 4 kernels will parallelly scan the image and generate a feature map each. The 4 feature maps will collectively form the representation of the image. The accuracy of this model was close to 95%, indicating that it is pretty good at differentiating between all of the numbers. And if you look at the different feature maps it produces for all of the numbers, you'll see that it's quite diverse. Even between 0 and 3, where the one kernel setup was failing, you can see that this one doesn't. The third kernel, for example, which looks for diagonal patterns, does indeed do a good job of distinguishing between the two. So a general rule of thumb is if you add more filters or more kernels on your conv layer, it can pick up more patterns and therefore be more expressive and less prone to underfitting. So we trained some 5x5 kernels, but what happens when we increase or decrease the size of the kernel? Well, intuitively, a 3x3 kernel will only be able to see a small 3x3 portion of the input image. So if you're just training just a single layer, it is unable to learn any global patterns from the image. A 7x7, on the other hand, can see a larger portion of the image and therefore learn more complex patterns because it is pattern matching a larger area of the image. But on the other hand, as the kernel size increases, we get more and more close to global averaging and begin to lose out on the low-level details in favor of the high-level ones. Having a quick look at the animations and the feature maps generated by the 3x3 and the 7x7 kernels, you can see that the 7x7 one looks more abstract because of how much it spreads out, whereas the 3x3 ones create feature maps that are more low-level features, like identifying specific edges and specific diagonals. So, in other words, a single-layered convolution layer with 3x3 kernels are going to produce feature maps that are too low-leveled, but it does have a lot of benefits if we increase the number of layers. In deep CNNs, we have multiple convolution layers arranged in series, and each convolution layer trains their own set of kernel weights. The input image first goes through layer 1 to generate a feature map, and this feature map is inputted onto the next layer to produce a new feature map. So subsequent layers don't directly see the original image, but they indirectly access it through the feature maps generated by the previous layers. Also note how the information propagates as the number of layers increases. So any given pixel on a feature map in layer 1 will have access to only the nearest pixels from the original image. But the next layer will have access to the nearest pixel of this feature map from layer 1, meaning that indirectly it is actually accessing a much larger patch of area in the original image. And this is why as we move across the conv layers, the network begins to pick up more and more abstract high-level patterns about the image because it's able to access the original image globally through these multiple feature maps. And as the level of abstraction increases, it begins to feel unfathomable for humans to interpret, and this is why the problem of the black box arises. And there's always this trade-off in deep learning. On one side you got interpretability, and on other side you got performance. As you make your models more and more complex, it becomes more powerful and its performance increases, but it becomes more of a black box and its interpretability decreases. I'll leave a couple of links and videos in the description below for you to study more about these stuff. So why have CNNs been so successful with images? The first and foremost reason is that CNNs induce an inductive bias into the learning process when it comes to an image. By aggregating information from a patch of nearby pixels, it is telling the neural network that learning the correlation between nearby pixels is more important than the correlation between distant ones. And that property of feature locality allows the network to be constrained in what it can learn because the models don't need to pattern match the entire image at a global scale, but instead find repeating patches throughout the image. Secondly, because we are scanning for the same patterns throughout the image, CNNs train less number of parameters compared to a fully connected neural network or a transformer-like attention model. And thirdly, because of the inductive bias and lower number of weights that a CNN train, they tend to be a little more data efficient. It's less data hungry than standard neural networks. Now, in theory, if you have infinite resources, infinite compute, and infinite data, then a general neural network architecture like MLP will end up performing the same as a CNN. But on less data, the general network has to spend some time learning about feature locality and pattern matching simply through backpropagation, which the CNNs just get for free, thus making them more data efficient. And the fourth advantage is the concept of translation invariance, meaning that even if the objects in the image are slightly shifted, with enough training data and augmentations, the CNN will learn to be robust to these changes. And this is specifically true when we undersample the images with, say, the strided convolution that we showed earlier, or techniques like pooling. CNNs are not considered to be naturally rotation invariant, but when we train multiple kernels, they tend to learn the rotated versions of each other, which kind of makes them rotation invariants in an indirect way. Also note that CNNs are great for capturing the global information about the image, especially when we train really deep convolution networks. As the layers go deeper, each value in the feature map begins to have access to a larger area of the original image. And this information propagation scales as we add more and more layers on our convnet. And for this reason, deep convnets are great for learning global patterns, even if initially they rely on local features. And that brings us to the end of this video. In the next one, we will look at another great application of CNNs and how they can be used for image segmentation. And particularly, we are going to train a special type of CNN model called the UNet to segment footballers from real game footage. Do hit that subscribe button and the bell icon to stay notified when I release the next videos. And shout outs to my first ever batch of channel members and patrons. Thanks for believing in the channel. You guys are magnificent. Thank you.